of x. Any problem? No? So let me write phi plus of x plus phi minus of x, and then let me take summation over vector k h cross square c square upon v 2 omega k and a square root of all this times a of k e to the power minus I k x plus a dagger of k e to the plus I k x. Okay, so I would be using two different, I would illustrate it to you through two different things. The other thing would be dqk twice pi whole cube 2 omega k, and here it would be the same, and this would be the same. Okay, e to the power minus I k x a dagger e to the power plus I k x. Here I have put h cross equal to c equal to 1. Okay, so these are two different Fourier expansions of the field phi in two different ways. This first one is called as finite volume normalization. This one, second one, is called as infinite volume normalization. Okay, so in this one you would obtain Dirac distribution functions. In this one you will obtain the Kronecker deltas. Okay, this is discrete, as you can see. Okay, this is finite volume, this is infinite volume normalization. So one can use one at a time, but I just want to illustrate some point. And these factors, you see, in all of these decompositions, similarly here our normalization factors appearing here in the Fourier expansions of these string fields. Okay, here in the first one, let me call it the first choice, and or let me call it infinite volume normalization and finite volume normalization. So in the finite volume normalization, one would obtain a of k, a dagger of k prime, delta of k and k prime, and in the infinite volume normalization, so case 1 and case 2, here you will find a of k, a dagger of k prime. This would, instead of this, would be twice pi whole cube 2 omega k You see, the two results would look different. They are conceptually the same. These normalizations appear because of the normalizations used here. Okay, so I would work with the first one because of the very simple logic that I am going to use similar ones in the string theory. Okay, although for teaching field theory I many times prefer this one, so-called infinite volume normalization, over the first one, but the two are equivalent. Here things, they look little bit simpler because these normalization factors have been chosen in such a manner that when you obtain a and a dagger, you have just Kronecker delta, right? But here, instead of Kronecker, you will have this because of the infinite volume normalization. Okay, and these are the normalization factors. And so yet another check is to calculate the Dirac distribution itself, going from this side to that side and that side to this side. So one can make a few checks. I will perhaps not take all of them, but now let me go a little bit further. So I think we can at the moment ignore this completely, and we can have a look at this one. So now, so here you see this is phi plus of x, and this part multiplied by this, it would be phi minus x. So this is positive frequency part and this is negative frequency part. So positive frequency part involves an annihilation operator, right? And here look at this, this is the annihilation operator, and this is also the annihilation operator, and therefore I am calling it a positive frequency part, okay? Positive frequency part. So the but let me not mix it up with that. So, and this would be negative frequency part. And you will also, another important point you would encounter is that the normal ordering. Normal ordering in field theory. So what you do, supposing you have phi plus, a product of phi plus and phi minus, and if you want to normal order, this would involve an A, this would involve an A, and this would involve a dagger. Okay? By putting an object between two dots on both the sides, this is one of the standard notations to denote the normal ordering. So far this is not normal order. Now what you do is you take it, now you use the, because here we are dealing with bosonic case, bosonic field, bosonic string fields, bosonic string theory. So we assume that A and A dagger are bosonic, and therefore they would obey the commutation relation. So K prime. Okay, so what you will do is this would be A dagger, you can of course put the levels K and K prime. So A dagger of K, A of K, A, so this is A dagger minus A dagger A equal to this delta of 1. So A dagger is plus A dagger A. Okay. In quantum mechanics, this would be simply 1, or even when here, when K and K prime are same, this gives me 1. Okay. So this is usually referred to as the normal ordering constant. Okay. And here, so this is this A dagger A plus, let me say, now this, you see, A dagger A is a normal ordered product already. So what is a normal ordered product? A dagger by definition is plus minus A dagger A. Okay, so for bosonic and fermionic, means for if the A and A dagger were fermionic, then they would anti-commute. Okay, I'll come to it a little bit later, but what I want to, the point that I want to communicate here, if you interchange the positions of A and A dagger here, if they are bosonic variables, they do not pick up any extra minus sign, they just stay like that, but with a plus A normal ordering constant. Okay, but if they are fermionic, they would pick up the minus sign. So this is just by definition, you see, bosonic variables, they commute, and so this is AB minus BA equal to 0, whereas fermionic, so this is bosonic, and for fermionic variables A and B, they anti-commute. So A, B plus BA, and if they anti-commute, then AB plus BA equal to 0. This would give me AB equal to minus BA. So fermionic quantities anti-commute, bosonic quantities commute. So this is just a signature of that. But when we calculate the Hamiltonian of a quantized theory, at the end we also do the normal ordering. So by definition, in field theory as well as in string theory, it goes without saying that everything from beginning up to the end has to be normal ordered. So the results have to be expressed in terms of the normal ordered quantities, normal ordered objects, according to the standard rules of quantum mechanics. So which means the bosonic quantities would, bosonic operators would follow commutation relations, and fermionic quantities would follow anti-commutation relations. So in this, even in the next 2 days, in the next 2 weeks, whatever we do this semester, we are doing with bosonic string theory. But if we were doing fermionic theory or a fermionic string theory or the superstring, which we might do next year, then we would, these modes, instead of obeying commutation relations, they would obey anti-commutation relations.